We have the Milan Design Week, but on the same time, we have the Helsinki Design Week going on. That's why we wanted to exploit these two events and to promote the DateMats project, where we have several partners. We have partners from Italy, from Spain, from Denmark, from Finland, and am I missing someone? I think they are. So, and we have also special guests from Austria today, Tamara König from Design Austria, that will talk a bit later on about the experience they had in the fiber use project. So I would say I leave the stage to Venere Ferraro from Politecnico di Milano. She is the project coordinator of DateMats, and she will introduce herself and will introduce her, let's say, the project and the main aims of this project. Please, Venere.
Hi, good afternoon, everyone. So welcome to this joint event between Milano Design Week and Helsinki Design Week. So thanks materially for putting together these two events, and thanks to Piero from Aalto University for giving us the possibility to have this joint event between Milano Design Week and Helsinki Design Week. So I introduce myself. My name is Venere Ferraro. I am a researcher and a teacher at the design department of Politecnico di Milano, and I am the coordinator of this amazing project that has been a wonderful journey started at the beginning of 2019. The project is called DateMats, and today we are talking about how we can design with emerging material and technologies. Let's say a few things about the project. So what is the DateMat project about? The project focuses and is embraced into the name of the project about knowledge and technology transfer on emerging materials and technology through a design-driven approach. This is the core of the project itself, because materials and technologies have been exploited during all the years more into the techno or engineering side. So the reason why we approach this project was exactly to understand and give the value to the materials and technologies, not just from the performance point of view, but also from the language point of view, how to give the material their the experience, the sensorial experience and the dimension related to touching and experience the materials. And we are surrounded by material. Everything around us is made up of material, and of course it's one of the core of the creative industries. So what was the objective that we had in mind when we started this journey 3 years ago? Was to we ask ourselves how we can be updated, be informed, know, teach, transfer, how to develop, how to design with and for the material of the future. So the main aim, the impact that we wanted to have for this project was mainly to create a transnational network between university, research center, organization, together with the small, medium enterprises. So we had two main purposes during this project. From one side, it's a purpose related to the academia. So we wanted to implement and develop a new method, a new design method to design with the 4 new emerging material and technologies. So to teach the practitioner, the designer, the professional of the futures, and contemporary to understand how to transfer the knowledge that we gain in academia to the SMEs in order to fill the gap between academia and SMEs, and to understand which is the best way from the academia, from the research center, to communicate, to talk, to understand the proper language to communicate with SMEs. So when it comes to the materials and the technology involved into the project, we have four main areas investigating during this project. And I won't go in detail of these four areas because the expert involved in the project will give a talk later on. But just briefly, we have four areas that are linked to the university involved into this project. So we have ICS and wearables based material in design department of Politecnico, nanomaterial for Matterfad, wood-based material at Chemart's laboratory at Aalto University, and advanced growing material at KEA, at Material Design Lab of the School of Design at Copenhagen. How we approach this project, which were the activities that we developed so far. So we did activities in parallel. From one side, we try to understand how to design with the new materials, how to develop new method, to test with the students, and to apply this method during workshop and during teaching activity. On the other side, we try to understand how to the needs of the SMEs when it comes to the relationship with the academia. So we try to understand how to contact SMEs, how to collaborate with the SMEs, and we did several activities. For instance, what we call the knowledge transfer labs, during which we explore how to use this new material and technology with the company. Where we are now? Now we are at this stage. We are almost at the end of the project. It will end up in April 2020 with the final events again during the design week, the next design week in April. But till the end of the project, we will have a lot of different activities, exhibition, workshop, and events open both to practitioner, designer, and companies. These are in detail all the activity that I was telling you about before. I would like to focus on two main activities that gave us the main result of the project. So as I was saying, we developed these knowledge transfer labs. We invited companies, professionals to join our researcher in a series of free innovation workshop. We developed this workshop in the different countries. So in Sweden at the Material Connection headquarter, at Barcelona Design Center in Spain, at Material in Milan. And what we wanted was to let the participant, the company, to explore the material. And we did a workshop by using a design thinking approach to let them understand the potentiality of this material, and we also did a generative session, an idea generation session, in order for the company to understand the possibility for area of innovation. And then we gave the possibility to the companies involved during the knowledge transfer lab to be part of our manifesto. More than 50 companies enrolled and signed for the manifesto and are now part of our transnational network, thanks to which company can be updated about the results of the project, but also about the advancement of the research in the four main areas at the core of the project. And of course, this is also a great occasion for the company to create networking and to have the possibility to be in contact with companies developing different kind of products or services. So together with this activity related to knowledge transfer to the company, we asked ourselves how to design with for this this innovative area of material and technology. So we started understanding the different mindset when it comes to shaping, using and applying this former area of materials. And for sure, a designer that wants to approach this area has to need to have certain kind of expertise, understand the challenge behind the use of this material, the context, and of course, the different area with which you have to collaborate. You will see later on how this area of material connecting to other area rather than design or material, so chemistry, computer science, or sustainability. And then knowing, going deep into the peculiarity of this area, we developed this new method that is not just a teaching method to teach the student, but is a way to design. So it's both a design method and design teaching method. So what we understood by going deep into the features of this four area of material is that in order to approach it, you have to go through three main areas: understanding, exploring, and applying. So understanding is based on the body of knowledge, theoretical knowledge of the area. Exploring is related to the exploration, hands-on activity, experimentation related to materials. So in order to grasp the potentiality to design, you have to touch the material, the geometry, the quality, to experience the material. And just when you have understand and explored the material, then as a designer, as a professional, as a practitioner, you can have an idea of how to translate this material in a shape, by giving shape that could be every kind of things, from a bottle to a chair to a table or to a piece of clothing. Going to understanding contemporary also the manufacturing process behind it. And we will see when the expert will explain the four areas, how different are going to be this transformation, the exploring and applying activity related to this area. And what we did was to apply this method during what we called the International Emerging Material and Technology Challenge. So we did, so far we have done 3 international challenges at Tecnun, University of Navarra, at here at the design department of Politecnico di Milano, at KIA, where, and of course, this was a learning experience that involved teachers from the 4 universities, students from the 4 universities doing hands-on experimentation, design activity, and we had partners, we had companies that launched the brief that was according to which the students had to develop the project. And of course, the great innovation behind it was the multidisciplinary setting, because we had the student coming from product design, but also fashion design, but also mechanical engineering, but also computer science or design for interaction. So we had the possibility to understand during a practical activity the skills required for designing with such areas. And these are just few images of the workshop that we have been doing in the last month. And all of this workshop involved at least 5 companies, with 1 company launching the brief. Another important things that we develop as output and outcome of our project is what we call the EM&Ts transfer toolkit. The toolkit supported the students, but also the practitioner and the company during the knowledge transfer lab in understanding, exploring the material. Indeed, we have this let's say material box that is divided actually into the area of the design method, because we have an area in which you understand the material, an area in which you know how to which are the processes behind the use of such a material, and how to, you have a sample so you can touch it, and in the end you have a section dedicated to the application of this material, in order for everyone to understand the characteristic, the processes, and the potentiality behind it. I'm going to an end. So if you want to know about the project, you can contact us at info@deimats.eu, and you can follow us at our social channel, and we have the website in which you can be updated about all the progresses of the project. And thank you so much for listening to me. And if I'm not wrong, now the stage is to Anke Passold from Kia.
Thank you, Vina.
Yes. Please,
Yes.
Anke, it's your turn.
Yes. Let's see if this wants to actually like PowerPoint and share. It's in the process. Yes. And it should be there. Perfect.
That's great, Anke.
Excellent.
Your turn.
Perfect. Then good afternoon to everyone. My name is Anke Passold. I'm a researcher and educator at the Material Design Lab at Kia, the Copenhagen School of Design and Technology. And I have the honor of presenting the first of the 4 emerging materials and technology areas, advanced growing. The definition of the area within the project is materials from a controlled cultivation of microorganisms that can be directly grown and or manufactured into their subsequent form, function, and performance by tapping into the organism's natural growth behavior. I will run through these different parts of the definition in the following presentation. And though this sounds like a very manipulative line of action, it is in reality a very close symbiotic relationship throughout the process.
Anke?
Yes.
Sorry to interrupt you, but you are not projecting anything but the first slide.
Okay, it's moving on for me.
No, it's not full screen, and it's frozen on the first slide.
Okay, it's moving for me here. Then I quickly have to see if.
Okay.
Has moved on.
Yes, now we are seeing the slide number 6.
Okay, I actually would like you to see slide number 3. Okay.
Technology is not always helpful.
No, not at all.
Maybe the others can switch off the camera so the connection is better and it should move more easily.
Do you now any chance see a bottle of beer on your screens?
Yes.
Yes, perfect. Good. Then maybe I just have to take it a bit slower when changing. So humankind is neither new to cultivating materials for specific use, nor to the integration of microorganisms in their daily activities. The first hemp cultivation go back thousands of years, where it was planted for fiber production, very much in the same way as one nowadays, again, is employing it for the use in textiles, products, and dwellings. And microorganisms, on the other hand, and the art of fermentation have been sourced in food making for beverages, and especially here in the north for preserving fresh goods for the cooler months, and in the Far East for allowing food to withstand hot climates, but also for the beneficial impact on health. I hope you see a new slide now.
Is still the number 3.
And this is not really. How about now?
Number 4.
Good, perfect.
Slow. It's a bit slow with the connection, but it's okay.
Okay, so what is making these growing materials advanced in the context of emerging materials and technologies is the controlled and strategic approach to working with the microorganisms and their respective fermentation processes, which can only be achieved through an in-depth understanding of their growth behavior, the necessary conditions, the possible combinations, and the resulting affordances that then eventually can lead to an array of different materials and then different application areas. This has, among others, been advanced through the enormous progress in our scientific methods and the related possibilities, but also to a big degree through the emerging interdisciplinary approach, where scientists and designers within this realm, typically material designers, are meeting to steer the development processes together. I'm going to try one more time. I hope you see a new slide. Do you have a new slide?
Not yet.
No.
Not yet.
Okay. It seems to work if I go out of the presentation and then go in again. Might be, maybe I should just not present it from full screen. You have to help me through if you see something new.
Well, if you agree, maybe we can afterwards share the presentation with the participants.
That would be okay. Yeah.
I think that could be.
Yeah. I'm trying to stop the video also, and
Now we see the number 5, Anke. So okay. Maybe you can X from the full mode, and you can just go on with the slide like this.
Yes.
Okay.
Perfect. Yeah. The collaboration does make a lot of sense between the scientists and the designers, because essentially one is working with something really, really tiny and therefore not very tangible, and processes that are not accessible without specialized equipment. So how does it actually work? Microbes and microorganisms ferment certain food, which means that they convert sugars within an oxygen-free environment. They do this to gain energy, to grow, and to divide. This process releases energy for the microbe, and from the microbe's point of view, both a residue and a survival strategy. For us, however, it results in a material opportunity, because it is these residues and material structures that we try to strategically harvest as not only food sources, even though there's a lot of advancements in this area which are beneficial for the material area, but actually as a material that we can source. Advanced growing materials is that are explored within the context of the project are mycelium, so different strains of fungi, bacteria, and as a growth aid and medium, yeast and algae. I trust that you're seeing new slides now.
We see the number 5.
This is
Anke, don't worry,
Yeah.
we will share the presentation afterwards.
Okay.
If
Okay.
you want to talk about, I mean,
So I just talk about it. I've now made it small, so I hope this might help. But I'm just going to talk through the rest of the slides because otherwise the 10 minutes is going to be eaten up by me trying to fix the presentation. So we have mycelium, which are the root structures of mushrooms, which are actually created by spawns. And through their digestive processes during their growth, they create a vast net which binds fibers into coherent structures. Depending on the substrate and the strain of the fungi, the resulting materials can create a wide range of foams and sheet materials. Softer foams afford great potentials within insulation and shock absorbing applications, for instance, as seeds and soils. Veronica, I don't know if you have the physical toolkits lying there, but I'm actually running through them. So otherwise they will be in the presentation, which I can send afterwards. Harder ones are explored for packaging applications or due to their acoustic properties for interior paneling. There are furthermore potentials as alternatives to leather and textiles. Bacteria exist everywhere and all around, on and inside of us. Here again, it is the combination of nutritions and the surrounding conditions that can create a very wide range of materials. They feed on sugars, to create a number of different materials, again with fantastic characteristics due to their compatibility with the human skin and non-allergenous nature, and yeast and algae in this context mostly as a growing medium, which can be created on substrates ranging from food. Food production residues such as the production of bacterial cellulose, where the fermentation process creates a cellulosic material of incredible strength. Applications range from packaging to skincare due to the dermatologically safe characteristics to paper production, here typically with an extra treatment or as alternatives to leather. Bacteria can also produce PHAs, a biodegradable plastic. Example here, which I trust you can't see. It is from a microbial fermentation of sugar beets, but PHA can similarly also be sourced from wastewater, effectively cleaning up whilst creating a healthier and more cyclable plastic. The approach to any such material creations is recipe-based, which is to say that the ingredients, the microorganisms in connection with the feeding substrate, the growth conditions, and the time become essential parts of the eventual product and are typically conducted in scientific lab-like settings due to the required sterility in the process. The production itself follows a controlled process of reasonably stable conditions for the outcome to be reasonably reliable within an industrial context. The physical manifestations of the results from the fermentation processes can thereby take very different constitutions, from mycelium foams and fabric-like materials to cellulose-based fabrics, mineralized constitutions, synthetically created silk threads, and even naturally dissolvable plastics that through the symbiotic processes can either be grown into materials for use in products or directly grown into the finalized shape, the finalized product, where the bioreactor directly forms the artifact functioning as a mold during growth, thereby cutting any additional production processes. In this context, microbes offer a great potential of vastly renewable biodegradable material alternatives that can be programmed and shaped according to need, and that even allow for tackling some of the human-induced challenges around the planet. They additionally have great potentials due to their skin-friendly, non-allergenous nature, which makes them applicable in many close to the skin applications. Working and designing with them affords a notion of creating in symbiosis with natural agents, for better and worse, because we also have to be aware of material variations in terms of structure, color, texture, which often conflicts with our current understanding of industrial standards, as well as the processes that we have established and the wish for scalability within the processes. And with that notion of symbiosis, I would like to thank you here from Copenhagen. I'm very sorry for the presentation not working. I will send it to you, Veronica. There's also an email included if you should have any further questions. Otherwise, I believe there's a Q&A forum at the end of the session. And with that, I give over to Pirjo in Helsinki.
Thank you very much, Anki. At the end, it worked. So
at the end, it worked. Perfect.
Well, let's say the last third was okay. But for sure,
Okay.
everyone appreciates if they can get the slides.
Of course.
Yes. Let's hand over the stage to Pirjo in Helsinki at, as we said, at the Helsinki Design Week. Please.
Thank you. Thank you. Nice to see you there. And I'm sitting in the middle of one exhibition here, so I just very shortly saw you around. So we still have the restrictions here, and we didn't have the full agenda of the Helsinki Design Week, but we have kind of satellite event here at the Aalto University campus, and that's where I'm sitting currently. And I'm going to talk a little bit of the experimental wood-based materials. And okay, I would like to share my screen, but yes, okay, thank you. Let's hope that this works now. Yes, here we are. So what do we mean by these wood-based materials, in fact, in our case? So those are materials that are somehow processed either chemically or mechanically from trees or other applications. So those materials, no, sorry, just wait a moment. So they are processed from chemically or mechanically from trees or other plants. So it's not only trees, in fact, but in our case, we have focused, for this project, we are focusing on trees and wood-based materials. And the idea is that, as you know, that this wood-based cellulose is currently used for different kinds of purposes already now. But what our idea is here that we should target to some innovative ideas and more high added value applications than only toilet paper or packaging materials. So we work a lot with cellulose fibers, but also fibrils, micro nanostructured, and the different kinds of derivatives, and also with lignin, bark extractives, and novel combinations of these. We are, well, first maybe a couple of words of what this cellulose is and what does these lignocellulosic materials mean. So cellulose is the most abundant organic polymer in the earth. So it is everywhere. It's in wood, it's in plants, it's even in algae. And of course, it can have very different formats. And that is exactly what makes it very interesting. And it is renewable from renewable sources. It can be recycled several times, the molecule itself. And it can be functionalized through different kinds of methods for different kind of purposes. But it's not only cellulose that we can have from the wood, it's also, for example, lignin, the brownish thing here on the left. And of course, different kinds of fibers also, long fibers from the bast fibers from the bark, for example. And then different kinds of colors, different kinds of extractives for maybe to replace also certain kind of chemicals in the future. And already now there are certain applications existing. Here is, in fact, a tree showcasing the how these materials come from the log. If we start from the tree and then we go to the log, and through different mechanical or chemical processes, we can achieve different kinds of materials that can be then used for different kind of purposes. And if you in fact, you can also, Anke was talking about growing materials. So in fact, you can see here the microbial cellulose also, which is it reminds cellulose grown by plants, but it's as it can be also grown by microbe. If you want to read more of this, you can also, we have made a cookbook of these materials, and in fact that's where these infographics come from, and it's also something that you can just download from the web page. These are some examples that we are working here with our students. So our main focus with this ChemArts activity is to focus on students and from different disciplines, and how they can work together and how they can learn from the materials, how they can be inspired by the materials. And these are just some examples here, like we've been working now already 10 years, and different kinds of composite materials, transparent materials, we can have hard materials, soft materials, or even this kind of flexible or leather-like materials. But as you notice, these are only the first ideas. They are far from any commercial applications at this stage. Here are some examples of the research projects. Even these are neither commercialized yet, but just to give you, open up a little bit of the realm of what's going on in the research. And here are some examples like casted wood. It's sawdust material that is, in fact, it's like wood, but it's casted and it's made of sawdust, and it's sawdust and nanocellulose, certain type of nanocellulose. We have here structural color. I really recommend you to familiarize with the Structural Color Studio. It's a super interesting project where they develop, the multidisciplinary team develops this idea that we don't need specific pigments on the materials anymore. It can be just the structures, and then they will form the colors. We also work a lot with recycling and textile fibers, for example, and then also with very futuristic ideas, for example, how to make bio-based optical fibers. What is also happening here in Finland is that we have become a kind of a hub for new type of wood-based textile fibers, and we are working with the ion cell technology here. You can see the photograph dresses made by our students. It's not a commercial level yet. It's still on a technology is validated in lab, so it's TRL4 level and moving towards a pilot scale. But we've been experimenting a lot with those materials and technologies at the university, together with our partners, of course. This is always interdisciplinary collaboration. But what is also happening here, that there are several other companies, or already companies, not only research projects, that are somehow related, somehow aiming to produce these textile fibers out of wood, or to recycle cellulose-based materials such as cotton. So there is those ones you can see on the left side. Very interesting times in the textile sector currently. And also some example, even more innovative and high added value ways of using wood-based materials. So this, where you can see this green like Sulapak here on the left, that's in our toolkit also. So we have selected a couple of these projects in our toolkits in this DateMats project, and Sulapak is one of them, and IOCEL is one of them. And it's so nice to see how these early stage ideas then little by little go forward, and these materials can be used in cosmetics, in healthcare, for medical purposes, etc., and of course for packaging. But this is my final slide, and what is the key thing? We are building on sustainability and circular economy strongly, and we always need to remember that nature is precious as such. So whatever we take from there, we need to really consider all the implications and try to act as sustainably in different ways. Of course, that's not an easy thing and not a simple thing, but that's something we also want our students to in their hands-on work to learn about materials and feel that they can impact and they understand where things come from and how we can together build a more sustainable material world. Thank you.
Thank you very much, Pirjo. It was really, really interesting. And greetings to Helsinki. I hope
Thank you.
Design Week is going well and people are finally going out and visiting all these interesting places you have there.
I hope same there in Milan.
Yeah,
hopefully
I have
you
to
are
say
doing.
here, maybe I can show quickly. There is quite a lot of people around, and yeah, unexpectedly a lot of people. We are really happy, and I have to say also DateMat project is having quite a lot of success. Okay, thanks, Pirjo. Now I will pass the word to Robert, which will go a bit deeper into details about materials, let's say. We are going on a nanoscale, which is another very interesting area of emerging materials. Please, Robert, the stage is yours.
Thank you, Veronica, Pirjo, and Anke for your presentations. I'm going to try to share my screen. Hopefully I will have luck. Please let me know if you can see.
Yes.
Okay. Well, welcome everyone. My name is Robert Thompson. I'm the scientific director at Materfad. Materfad is it's a center located in Barcelona. And what we have is a huge collection of materials that are used for innovation purposes, that are used for creating new opportunities for sustainability and hopefully a better world in terms of materiality. I have the daunting task of presenting to you something that is actually very difficult to present. It's very difficult to present because it is effectively a type of material which cannot be seen. And not only can it not be seen, but many times it cannot be sensed from our original organic physical body senses. And so my presentation will be very practical. I will focus it more on a general presentation of what nanomaterials are, their sizes and their properties. And then I will quickly move into some materials that you will be able to find in the toolkit, which represent some of these characteristics. Okay, so let's get down to the matter. So why is it so difficult to talk about nanomaterials in general? Well, the reason is because, as I mentioned earlier, we're talking about materials that are in almost a quantum scale or quantum state. So what does that mean? It means that the size of the materials that we are concerned with is so small that they cannot be seen at all. They cannot be sensed except with the presence of an electron microscope. Now here, I hope you can see this relative size chart. Nanomaterials fall way below the scales that we're normally accustomed to. Here we have ribosomes, we have protein antibodies, and right here on the level of 10 nanometers, which is 10 times the scale which we're concerned with, we have quantum dots, which, as you can see, have different colors. And we're talking about a scale of 10 to the minus 9 meters. That equates to about 1 billionth of a meter. Now, to give you an actual, more quantifiable experiential scaling of nanomaterials, we can imagine a nanomaterial or a nano composite to relate to a basketball, as that basketball would relate to the entire size of the world. Okay, so that's the scales that we're talking about. And therefore, what can we do on these scales? Well, on these scales, it's amazing, but through chemistry and extremely precise industrial processes using photons, electron beams, magnetic resonators, and things of this sort, we can manipulate matter at that scale. And so chemistry is obviously a precursor to nanomaterials because chemistry has to do with chemical compounds, which are at the nanoscale. So assuming that we can take these materials and build them up then we can actually have what's called a bottom-up approach. Bottom-up approaches are very different from top-down approaches, where we generally, in the top-down approach, take materials and reduce them, we sculpt them. The bottom-up approach, instead, is we're taking molecules and using their properties of electromagnetic attraction or repulsion, they can agglomerate, and therefore they can form these particles. And as you can see, there's an enormous amount of different forms and shapes that these molecules can take. Now, here's where the complication comes in, which is the shapes of these molecules are dictated by the processes used to make them, but they're also dictated by the chemical compounds used to make them, like carbon or nitrogen or oxygen. So you can imagine that in the future, and already today in the present, there exists a humongous amount of variable options in terms of shapes, in terms of sizes, and of course, in terms of states, which means that we can make materials that are nano-structured that constitute individual particles. They may constitute fibers, or they may constitute foams, or even layers or crystals. So you can imagine that there's a huge diversity. And just to take a look, here's a dendrimer. A dendrimer is a type of molecule, like hydroxyapatite, for example, is a dendrimer, which means that we have maybe a center molecule and then we have growth on the sides. We can also have liposomes, which is very typical of viruses. We can have hydrocolloids, or nanoparticles of hydrogel. We can also have carbon nanotubes, which are very kind of, in the spotlight nowadays. We can have also gold particles, et cetera, et cetera. Okay, so without boring you too much on these details, I want to make an extremely important differentiation, that no matter how we use these nanoparticles, the major difference that we will obtain is a physical one. Meaning that if we use these nanoparticles inside of another material as a reinforcement or as a additive in a substrate, you will have one type of effect. And if you use it instead on the surface, you may have a completely different and revolutionary other property in the material. So the first differentiation we must make is where it is used in the material. So as you can see, we're compounding on this complexity of, depending on the composition, depending on the size and shape, and then it depends on also where we put it. And here we have an example of Tough Guard. Tough Guard is a type of treatment, which is a nanoparticles that can be put on top of a surface of any type of material, polymer, metal, ceramic. And what this does is it increases the performance of that substrate by adding a hard layer, which is, for example, non-water soluble. And this can be done in many regards. But another aspect is, what if we took these particles and then we put them inside of a material, such as something like this? We have a 3D ion conducting ceramic network. What does that mean? It means that the blue material is a ceramic, which has its own individual properties, its resistance, its hardness, its beauty, its acoustics. But then embedded inside, we have these nanofibers that are interwoven into a matrix. And maybe these fibers are electrically conducting, in which case we get a ceramic that has electrical conductance. And so you start seeing how nanoparticles or nanotechnology can actually change the face and the behaviors and the properties of materials by their integration. Now, how does this happen? This has often puzzled me because it's really, really strange. But in reality, nano, what it means is that as you get smaller and smaller particles, you get more and more surface area, as you can see here. This is a block, 1 centimeter by 1 centimeter, and then we divide it into millimeters, and obviously we get these tiny little blocks, which each one has the same amount of volume same amount of surface to volume of the initial one. So we have a multiplication of the surface, and then we bring it down to the nanoscale, and now we have 1,000,000 times or even more the surface area. Now in chemistry, this is important because electronic exchanges, chemical reactions, heat exchange, magnetic forces occur across surfaces. So what this means is that nanoparticles, when they're so small, they become extremely performing in terms of their original properties. And of course, we can also grow nanomaterials on surfaces, as you can see here. These are carbon nanotubes that are grown on gold particles, and they create these forests of surfaces that are nanoparticle based. And these nanoparticles of carbon can be used like as a sensor, for example. They can be used to trap light. They can be used to trap bacteria or viruses. And so now we start seeing that within the paradigm of the materials, we're actually designing properties into a material using nanoparticles. And these nanoparticles are not visible, which means that it's almost like magic. We can put these nanoparticles on surfaces and completely change their properties. Of course, the applications are very numerous. Here I just have a few, but one of them is pollution removal, or maybe we change the way that we do biomedicine, or maybe we use this as a catalyst. Of course, to everything there's a cost, which is nanoparticles can be cytotoxic. And so let's take a look at some of these materials which are, let's feature it in the toolbox. Phoenix MTM is a high pressure laminate sheet, okay? This is a very flat material. It's very lightweight, extremely rigid. It's textured on both sides. And it has, within the glue, it has these nanoparticles that are fillers, and they are cured in this acrylic resin using an electron beam, which means that this surface can be extremely squashed, really flat, really rigid, and high impact, low crack propagation, and we can use them, for example, in any idea like incredible industrial packaging or long life packaging, or maybe doors for an airplane. Of course, because they're flat, they need to be cut. And so there are limitations with some of these materials. This is a flat material, rigid, and so if you need to make something complex, well, you're going to need to somehow cut it up into sheets. Another contendant is the graphene. The graphene is extremely important nowadays because it's a new material. It is incredibly electrically conductive. It is incredibly light. It is completely invisible because it is based on carbon-carbon junctures. This is a flat sheet of pure carbon, which can be flat, applied to a surface. It can be rolled up into a tube. It can be a multiple tube within a tube. It can also be fibers that are cones stacked within each other. Here you can see some pictures of these structures. Now, why would we use them? Well, because graphene has a tensile strength of about 100 gigapascals. 100 gigapascals is about 10 times stronger than the highest alloy steel. So you can imagine that if we put these fibers within a polymer, we can obtain a polymer with relatively similar properties to a steel. And so that's one side. And then the other side is these carbon nanotubes have a Young's modulus, which means of the rigidity of one terapascal. 1 terapascal is an enormous amount of rigidity, which means that we can make products like rackets or skis or even a helmet that has very lightweight properties, but is extremely rigid and strong. But the best part is the thermal and electrical conductance, which means that we can create composites using these carbon nanotubes that can conduct electricity through resins, through metals, through glasses, through any kind of mineral. And here you have an example of what the electrical conductances of these materials can be. Another aspect of this is the heat conduction. So we can have materials that can conduct incredible amounts of heat across very thin platforms, which means that we can create products that are made out of polymers that are behaving in no way like a polymer because of the rigidity and their electrical and thermal conductance. But of course, graphene is a nanofiber, and if we don't recollect them, they can be lost in waterways and they can contaminate biological systems. Another aspect of nanotechnology is cleaning, okay? For example, Bionox, this material you see here, is a material which is infused with a paint that contains titanium dioxide, and titanium dioxide is a molecule which has particular characteristics of being able to act as what's called a photocatalyst. What is a photocatalyst? A photocatalyst is any type of chemical that uses sunlight as the primary source of energy, uses oxygen as a molecule to conduct what's called a double substitution. And in that double substitution, it can convert, believe it or not, nitrous oxides, or NO, or carbon monoxide, which we know is not healthy, into nitrates and carbonates, which are completely non-toxic. And these can be used, in fact, by plants. In fact, Other aspects of these photocatalysts are that it can destroy within minutes certain bacteria, certain viruses, and also certain fungi. So think about this in applications of packaging, for example, or medical equipment. Unfortunately, some of these materials can create ozone layer or ground level ozone or GLOs, which can affect plants. So we must always remember that using nanomaterials, there are always the double-sided, the other aspect of the coin. Second to last material I'm presenting is nanoclays. This is another aspect which is very interesting for you to research. Nanoclays are clay-based or silica-based particles which can be included inside of any other material, and it will increase the hardness of that material. It would also increase the mechanical stability of that material, especially under heat, which means that we can introduce ceramics at a nano level within materials that normally melt at one temperature and drastically change that melting point. And therefore we can give that material a huge advantage in terms of thermal resistance. Okay, so I'm approaching the end here. One of the more commonly known approaches to nanotechnology is the waterproofing aspects. Now, silicon dioxide or these complex chemicals which can join together to form these ethyl silicates, which is this molecule here, they can be bound to the surface of a material. They look like these little spheres actually under an electron microscope. And what they do is they impart on a surface a very high complexity of a terrain. And that high complexity of a terrain reduces the water tension on that surface. And therefore it creates what's called a super hydrophobic property, which means that we can take cloth, we can take leather, we can take many different types of materials and add them to the surface. And now, bang, you have a surface that is resistant to water. Not is it resistant, it just literally repels water because water has a higher surface tension than it. And so by doing these modifications, we can actually make products that are more interesting because they can resist water, they can self-clean, they can create non-fogging surfaces, they can create non-corrosion or corrosion-resistant surfaces on metal, and we can save on the manufacturing process. So I hope I didn't take too much time, and you were able to understand some of the basic principles of some of the very numerous opportunities that there are in the nanomaterials. Thank you very much.
Thank you, Robert. Thank you very much for this great presentation. It was very interesting. And so now I would pass on the stage to Stefano from Politecnico, who is now somehow combining different materials to a material system in order to create interactive, connected, and smart materials. But I leave the stage to Stefano, who for sure is much more informed about the topic. Thank you.
Thank you, Veronica, for the introduction. Can you see the presentation full screen? Okay.
Yes, we do.
Okay, perfect. So good afternoon to all of you. My name is Stefano Parisi. I am here connected from La Materioteca, the materials library at Politecnico di Milano in the School of Design, close to the School of Design. I am a research fellow at the Politecnico di Milano Design Department, and today I am pleased to introduce the topic of ICS materials. I am involved in the DateMats project, and I am also part of two research networks called Materials Experience and DIY Materials that are interested in exploring the potential of emerging materials for design in terms of applications, practices, and experiences, and that they enable and imply. In the project DateMats, we, the Politecnico team, specifically are focusing on the emerging areas of interactive, connected, and smart materials, also known with the acronym ICS or X materials. X materials are defined as systems combining inactive materials, stimuli-responsive smart materials, and embedded sensing, computing, and actuating technologies. They can sense and communicate data from the body of the user or from the environment, and they can perform some behaviors. For example, shape-shifting behaviors, so they can change their shape, light-emitting behaviors, or color-changing behaviors. Among the different potential applications, one of the sectors where these materials are more exploited is the one of wearable technologies. These materials, in fact, can be embedded into clothing or worn on the body as implants or accessories. And when integrating into textiles, we call these textiles electronic textiles or e-textiles. To have a clearer understanding of what ICS materials are, it is necessary to consider these materials as hybrid and complex systems made up of several elements or building blocks. By combining these different layers or building blocks, they gain and play out their smart, interactive, and connective capabilities. The first layer on top is the one of the material support itself, the inactive components. They are conventional materials with no evident interactions, such as paper, plastic, and textiles, and other materials. They can be used as a support and structure in the system and provide the material properties, for example, stiffness, flexibility, and resistance, and the material qualities, transparency, opacity, color, texture, and many others. Indeed, they interact with the technology by enhancing or characterizing the resulting behavior and the appearance of the material, aesthetically and functionally. The second layer is the one of the sensing materials and technologies. When they are embedded into the materials, they allow to sense inputs from the users or the environments. They include sound, touch, and proximity sensors and other technologies. They can also include the conductive materials that can be used as a sensor in the form of inks and yarns. Actuating materials and technologies is the third layer. They include the embedded actuating technologies such as LEDs, buzzers, vibration actuators, and also other kind of actuators, but also reactive components, including smart materials, the ones that have changeable properties, the one that can reversibly change some features like shape, color, or light emission in response to physical or chemical influence from the environment or from the user's body. For example, temperature, light, pressure, mechanical stress, electric or magnetic fields, chemical elements, and compounds. These technologies are connected with external or embedded computing technologies like a microcontroller, such as Arduino or Flora boards, which is the case for prototypes, or custom boards for products. The interconnection between the components is supported and enabled by additional materials that can be found in the system. The conductive materials can substitute the traditional wires and cables, and they are mainly made of metal like silver, copper, or can be carbon-based like activated charcoal or graphite, and can be found in the shape of conductive fibers, threads, printed circuits, paints, and coating. To make the system functioning, we also need to provide power through electricity. Instead of plugs and batteries, alternative sources of energy can be integrated as additional components. These can be embeddable power supplies like flexible batteries, electricity generating materials such as piezoelectric ceramics and polymers. On applying mechanical stress to piezoelectric materials, they generate an electric current. By combining the different layers of components, it's possible to obtain passive systems, active systems, or proactive systems. What you can find on the market usually are passive systems that are able to sense and active systems that are able to act. But by integrating passive and active systems in a design solution, it's possible to have what we call proactive systems that are both able to sense and react. And more importantly, they are able to respond to the users' behaviors, to communicate some information based on that behaviors. And in this way, they make the user to behave and respond in response to it. Let's dive now into a series of selected commercially available examples and prototypes from designer and researcher labs divided in categories. Conductive materials can be used to create the interconnection between the layers. They can be made by printing material inks, conductive material inks on other surfaces, for example, on plastic and fabrics. Currently, the technology provides flexibility on single curved surfaces, but the research is focusing on providing even conductive materials that can be positioned and can support elastic materials or can be positioned on two curved shapes. This way it would be more practical and comfortable option to be worn by the user. Woven conductive yarn can be used as interconnection between components and also for touch sensing. This way it can be used as a user interface for smart clothes by constructing an embroidery circuits. Woven conductive yarns can also be used to fabricate a flexible push button that can, in its default state, makes no electrical contact with the circuits, and only when the button is pressed down, it makes an electrical contact with the circuits, and the circuit is closed. Woven conductive yarns and tapes can be also applied on textile and can be used on as a sound amplifier when approached with a magnet due to their magnetic properties. Another category is the one of the shape-shifting materials. The shape-shifting behaviors can be easily induced by using shape memory alloys like nitinol, flexinol, muscle, and also muscle wires and threads. And this allows these alloys can be deformed, and when they are stimulated by heat or by electricity, they change their shape into a predetermined one, a preset one. And by exploiting this behavior and connecting them with other components, it's possible to obtain garments that change their shape according to different external inputs. For example, on the case on the right, they can change their shape according to the visual expression of the person that is in front of the user. Flexible, durable, and washable textiles can be integrated with the light emitting diodes, the LEDs, to produce some light emitting fabrics, and can be exploited as illuminated apparel and accessories. These smart fabrics are sewn or woven with intricately embroidered conductive yarns and miniaturized LEDs. The example on the right is called sun fiber, is made of an optic fiber with some LEDs on one bottom, and it is integrated into the fabric. And it is applied to technical garments in sports and safety application to allow long distance visibility for the user. And the last category is the one of the color changing and pattern revealing textile that can be obtained by using thermochromic dyes and coating on the textile. When they are excited by heat, they change their color or reveal a pattern. The example on the left is connected to a sound file and change a color responding to it through soft circuitry that are woven into the fabric, while the example on the right responds to user proximity and to the touch of the user using proximity touch sensors. Talking about what are the limitations and the challenges of these materials, one crucial gap is currently the lack of miniaturized technologies and batteries in smaller size and thicknesses, allowing the seamless integration into all kinds of materials. Another gap is the flexibility of technologies, allowing flexible and stretching when integrating to wearable. Also, another limitation or challenge is the one of people acceptance. So besides technological aspects, one emerging crucial challenge is identifying meaningful and purposeful ways for designing with and for these materials to meet the user's acceptance and appreciation. Also designer must ensure that in achieving what is technically feasible, the well-being of people is preserved and the requirements of wearability, human movement, comfort, and washability are respected. And the last challenge is the one of sustainability. So to deliver an environmental friendly final product using non-toxic, renewable, easy to disassemble, long-lasting and recyclable or compostable components. Regarding the opportunities, I like to refer to ICS material as a platform, as a playground where components can be combined in different ways to produce very different results, sensing to different inputs and translated in different behaviors. They are mainly, as I introduced before, applied into the wearable technologies sector to elicit aesthetic enjoyment by triggering the effect of surprise by creating multi-sensory experience, but also they can support the user by a functional perspective. For example, they can monitor support body activities, they can be used for health prevention and rehabilitation, and they adapt to the user's needs for their well-being. Besides the e-textile and wearable technologies, there are many other potential application fields like furniture, interactive environment and buildings, and automotive. Having these challenges and opportunities in mind, the students of the School of Design at Politecnico are encouraged to take part of the challenge of their sustainable and smart inclusion into everyday practice as a catalyzer for change. And we are confident that these will positively contribute to fulfilling technological challenges and mitigating and solving societal and environmental issues today and in the nearest future. The students at our school experiment with interactive materials and generate concepts in workshops and courses. One example of these concepts are the garments with sensing and light emitting capabilities resulting out of the interdisciplinary challenge workshop hosted in Milano last July. If you want to know more, we recommend these open publications available online that are the results. One of these is the result of the DateSmart project. And if you have any questions or curiosities, I would be very pleased to answer in the questions and answer session later on.
Thank you very much, Stefano. As has been saying in the chat, it was a very interesting presentation. So now I would give the floor to Tamara Koenig from the Fiber Use Project, which has a booth here at Milan Design Week, right? Some couple of meters over there. So for the ones that are in Milan, come and visit DateMats, but also, and let's say materially and its materials village, but also the Fiber Use booth. So I hand over the word to Tamara.
Thank you, Veronica. Thank you for the invitation in last minute and to get to know you. In fact, Fiber Use and your projects have a lot in common. I also brought here Giacomo of the company Riverasca, who is also a partner in the Fiber Use project. I'm Tamara, I'm project manager for Design Austria. Design Austria is an interest association of designers, and we got designers involved to deliver concepts for new products made of recycled glass fiber and carbon fiber reinforced plastics. And Giacomo was helping to produce those products that are on showcase here now at Milan Design Week. Fiber Use is a Horizon 2020 project. It consists of 20 partners from 7 countries. And the starting point, where the exhibition is showcasing also the starting point, the initial idea of the Fiber Use project, as well as its results. It came from the fact that there is a huge land mining problem within the European Union of used end-of-life wind blades, and how these materials can be disassembled and reused again. So the product showcased at Milan Design Week in the Fiber Use project, they show products that are made of 100% recycled compounds from the wind industry sector. And where the project is finished at the end of September. So we are happy now that we achieved a lot of successes, but challenges also in communicating between engineers and designers. And I've heard about the challenges that you faced from your previous presentations, and we had a lot of common issues here in what kind of information designers need from engineers and what do they need to successfully work together. So I would very be interested to keep in touch with you and with your results in order to overcome those challenges in communication, basically, because there is a lot to do in terms of dissemination of project success if you make results as approachable as possible to a larger audience, and also to students and also to already professional designers. And I like Giacomo as the material expert here to say a few words about his experience in producing.
Yeah, thank you. I hope you can hear me. Thanks, Tamara. Thanks also for inviting me. Yes, I'm an engineer, mechanical engineer, and I work really hard on technologies and the fiber use project developed 11 technologies for the mechanical recycling and one quite innovative for the thermal recycling, thermal chemical, sorry, recycling of composites, glass fiber, carbon fibers, and actually I do agree with Tamara. The two projects are really close, and I really hope that we may do something in the future because we reach some results that are exploitable in an industrial level, and so maybe we may have a very good collaboration for real business, let's say. Thanks.
So if you have newsletters, Veronica will be so kind and send and type my email address or send my email address to all of you who have registered. And please put me on your newsletter list and keep us informed about your activities and your ongoing project results. I don't see any of you now, but I'm waving goodbye.
Yeah, maybe.
Best greetings to.
Hi.
Hi.
Thank you very much. Of course, we can share results and build collaboration for the future.
Yes, please, let's do so. I mean, we've gained so much experience and so many so let's have a synergy. And I'm really happy that it worked out for us this time for Milano, that it takes place and we are all present. And greetings also to Helsinki, that Helsinki Design Week takes place. And it's nice to, well, next time we hopefully see you all in person, but it's also good that the design weeks are starting place again and that we have this opportunity to meet you all online, because otherwise we would have never met. So I'm really grateful about this.
Yes. If you have still 5 minutes left to stay with us, maybe we can have a short questions and answer round. For instance, one question that me personally, knowing DateMath and the Fiber Use project, I wanted to ask you, what was, I mean, in the project you involved also external designers to develop some prototypes and some design concept. Okay. What was the main issue related to these recycled materials to, let's say, translate information about these new materials? Because I guess most of the designers never had worked with recycled carbon and the glass fiber composites. So where were the the big issues?
As soon as we said it's an EU-funded project for circular economy involving design and circular orientated design, many designers were completely up for that, and they said, give me more information. And at that point, we didn't have the information, and designers were asking questions, what can I do with that recycled compounds? Can I foam it? Can I make it softer? How hard is it? It used to be a wind blade, a rotor blade, but now what can we do with it? Can I take it in my studio and can I process it? Or what is possible? And we said basically everything could be possible. It depends on the machines, but it's also vague. It was very vague at the beginning, and it took us a long time to develop a briefing that was good enough for the facilities to work out the products that we are showcasing now at the Fiber Use exhibition here in Milano. But Giacomo can help me here.
Yeah.
You were so much busy involved with producing and trials and errors.
Yes.
Giacomo, I have a question for you, Giacomo. Hi, this is Robert from Materfad. I'm very interested in the processes that you're using.
Oh, there's a noise behind us, and it's not us.
We thought it's the echo, but it's an alarm.
It might be an alarm also.
Yeah. Anyway, please.
Okay, yes. I was intrigued and interested about your processes for transforming, for thermochemical transformation of the materials to recollect the carbon fibers. I'm wondering, is it a pyrolytic? Do you guys use pyrolysis, or do you use like a a chemical solvent to recover the fibers?
Okay, actually, it's not pyrolysis. This is a patent, Italian patent of a small company called Corec, with a K and a C at the end. You can find easily. It's a depolymerization process based on the CO2 gas. So it's a sort of reactive gas pyrolysis. The innovation is using a reactive gas. And from the syngas, you can condense it and have some, let's say, chains of monomers that are still able to react in fresh systems, resin systems.
Okay, so I'm assuming that the fiber that you're able to recover is in its virgin woven state, or are you forced to chop it up into a stochastic kind of irregular pattern?
From over there?
If you succeed?
Yeah.
Sorry, I was, I lost your question, please.
The fibers that you recover, are they in their previous woven state, or are they chopped fiber?
Okay, it depends from which kind of waste you are dealing with. I mean, if you use a wind blade, you have for sure long fibers because they use woven roving or fabrics and so on. In that case, we grind the material before the thermochemical treatment. So to have, let's say, 10, 15 millimeters fibers that we gave to the thermoplastic compounding with polyamide and polypropylene. And basically, it's better to grind before the pyrolysis, let's say, than after, because fibers comes sort of a cotton, is not easy to handle.
Sure. Thank you so much. Very interesting.
You're welcome.
Okay, is there any other question? Someone
From
for the
the
audience?
Sample of a scrap. Yeah, this is a lamination scrap. You see the edges with the glass fiber and the laminate. This is a laminate for the cold sector, you know, like trucks and so on. This comes from my my production.
From the audience, someone that has questions now that we have all these material experts here. I guess that you are all intrigued in materials. So this is your moment, your opportunity to get direct answers from our experts.
I want to ask about the sustainability and where the nanotechnology, what was, one second, and the circular economy and the nanotechnology.
So Robert,
I only understood part of the question. Could you repeat the question?
Yeah, how sustainable is using like the technologies you were mentioning? I'm just asking about its sustainability. Yeah, if what is at the end of life of that material, for example, what will be happening?
Okay, that is a very good question, and it cannot be answered in a single sentence. Your concern is very real. Nanotechnology, because of the sheer scale of it and the undetectability from a physical standpoint, is dangerous. And that is one of the reasons why it is being applied so scarcely still in the sector, despite its advantageous properties, especially on a surface level. So for us to be able to truly reel in the benefits of nanotechnology, there has to be a better logistics program put into place so that materials can be recovered and recycled in the very same industries that produce them or in certified industries. Can you hear me at all, or? Yeah, okay. So there has to be a logistics program put in place if we're going to use nanotech for sure.
Thank you, Robert, for your answer. Someone else? There is a comment in the chat. I'm going to read it out loud. This is fascinating. As a high school teacher, talking about materials from the 20th century looks like nothing like the materials for today and tomorrow. Thrilling. Oh, it's not a question, but I'm going to read it out. Thank you all so much for the work you do. Kids want to make positive change in the world, and having this information will give hope. Yes, I agree on this aspect. I think it will be also very important to, let's say, start teaching knowledge about materials from a, let's say, before university or high level education. Some other question from the audience? Direct question. Don't be shy and activate your mic.
Veronica, if I may, in the meanwhile, I just want to give a news to the audience because some question what about the toolkit. I just want to remind you that from the 7th of October, the EM&T project will have a great exhibition during the Barcelona Design Week. So you can have the possibility to touch with your own hands the different materials, and we will exhibit much more about the project itself. So be updated. If you check the website, you will see all the news and the upcoming events.
Yes, exactly. And as you just said, there will be other events like this upcoming, and for sure also the final event in April, where for sure we'll have quite a big exhibition and conference, and we have the chance to talk about these topics very broadly. As someone is asking in the chat about more resources and research on these technologies, for sure, you can find a lot of information on our website. So please go to the EM&T's website. There is a resource section where you can download also the deliverables we've created within this project. So best thing would be just browse through the website, and for sure you can also contact us via the email info@datemats.eu. I'm going to post the link now. Someone else wants to ask something. Otherwise, we are perfectly on time. So last chance. Oh, Stefano, great. You anticipated me. That's good teamwork. I want to add, I think we have a really nice teamwork in this project consortium. So thanks to all the partners that have been involved today and presented their knowledge in this very nice manner. Sorry for not being together, because that's the part we are missing most, I think, all of us. I have to say, as you can partially see, it's, well, beforehand it was really, really busy around here, so I was a bit worried about the audio quality, but I hope you enjoyed the event. And as I said, and Venera also mentioned, we will have others like this. So, so bye from Milano, bye to Helsinki, and Denmark, Spain, and I think there are a lot of people from everywhere connected. And see you soon. Thanks.
Bye bye.
Bye bye.
Bye bye.
Bye, guys.